Okay, so now I'm going to describe a way in which like you don't need to store xi or intermediate activations during the forward pass in a neural network at all. And the idea is very simple. So let's say that you have like a input xi, and then you made like a feed forward pass, and during like the forward pass your network's weights were like wf, and you computed like yi. Okay, so now the key idea is that if somehow you can train like a autoencoder in which like you can so you went from like xi via weight wf to yi, and somehow if you can like go from yi to x, if you can learn like this one-to-one mapping, then you can technically construct xi as you need it on the fly. So then in that case, like you don't need to store xi, but you can learn like this weight, you can learn like this backward network which can store like this xi. So let's like first recall like how does a standard autoencoder work. So the autoencoder consists of like an encoder and a decoder function, and the key point is like when you're like piping in your xi, you're getting like an intermediate activity yi, and if you find a way to actually go from like yi to xi again, and that would be like pretty cool. Okay, so now let's assume that when you're doing like a forward pass, your weights are like wf, and then you're trying to like reconstruct this output activity yi to like reconstruct like input xi. And so this is like the backward, this is like another kind of network through which like you learn like this decoder network which goes from yi to xi. So it turns out like the key expression for the weights of this backward network is nothing but like so basically here what you want is like you know that your yi is basically forward time for forward weights multiplied by xi, and then you want to go, so you multiply this yi by some network with backward weights wb, and you get back xi, right? So you can essentially substitute like this xi here. So you can so here like for example, using this expression, xi becomes wf inverse yi, and you can substitute this x back here in this expression, and what this gives you is wf inverse yi equal to wb times yi, and it tells you basically that a perfect autoencoder would be something in which like you start from your activities, and like whatever the weights are of your forward network, you can have a network which essentially constructs the inputs again from the output activities, and the weights on that network are essentially the inverse of the weights which are like of the forward network. So if we actually defined like a standard autoencoder in which like we computed like this, and then we reconstructed the input activities back, then we don't need to do anything. So let me talk about again like what will this kind of algorithm look like, and let's like talk about it. So like the key idea is that right now you are doing, so what is like the traditional algorithm which you are doing? You have like xi, you pipe it through your network neuron I, and then you get yi, you compute like the difference epsilon with respect to target, and then from this yi, like this epsilon, whatever you have computed, you do xi plus epsilon, and then you forward it through your network again, and then you get like yi dash, and yi dash minus y is basically the error signal of this neuron. This is like the algorithm I discussed till now, in which xi had to be stored in memory. So now we want a way to like get rid of this xi, and what we can do is, let's say you have like 5 layers in a neural network. What you can do is like you can pipe a network, you can pipe the input data xi, and let's say here you computed h1, h2, h3, h4, and then here you computed y. So now the key point is like you can, and let's say the weights on this network are wf. Okay, so you learned like a forward network like this. So the key point is that you don't when you are updating this particular neuron, you don't want to store these activities h4, h3, h2, h1 anymore. So these are like activities which you don't want to store. So what will you do is you will build an autoencoder. This is like going to be, so this network was was bottom up, because here the input is traveling from bottom to up, and then you can imagine that there is another network which is top down, and what it does is that it is consisting of like so if this has like 1 2 3 4 5 layers, it also consists of like 5 layers, and what it will do is it will take as input this activity y, and its weight will be wb, which is essentially the inverse of this forward weight wf, and here it will output like h4 again, and then similarly it will take h4 again as input, it will output h3. Similarly it will output h2, then h1, and this. So if you manage to learn such a network which is able to have like these backward weights which are essentially like the forward weights but inverse of them, then technically you can you can store these two kind of networks, which is like a forward network wf, a backward network wb, which is wf inverse, and then you can store like these forward activities, like you can compute these forward activities, and then as soon if you only have like this final activity y, it is possible to reconstruct like all the intermediate activities h3, h4, h2 as if like whenever you need them. So you don't have to store like all these four activities at the same time. You can start from y, you can compute h4, then you can compute h3 and delete h4, and then you can compute h2 and then delete h2, compute h1, and so on. So the assumption is that, so obviously this is a kind of mechanism where you have like a bottom up and a top down network, and the bottom up, like the top down network has weights which are inverse of the forward network. So now the key point is that the key takeaway from this is that you can get rid of like storing these intermediate activities by essentially involving like another top down network in which the weights are inverse of the forward network. But now let's talk about like the brain. In brain, this is not what happens, because let's say there is like a feed forward path, and then there is like a feedback path, which is like a top down path, which I also call as the feedback path. So the only perfect case in which this algorithm works is if the weights on the backward network are essentially the perfect inverses of the forward network. But like turns out like the brain is definitely not doing like these sort of inverse operations. So if you're doing it in a machine, it would work. Like you can do like if you have 5 layers and each one has a weight matrix, you can compute its inverse, and that will essentially be the weight of the backward pass. But since like obviously the brain does not do that and machines can do that, it means like there is something wrong which is going on. And what will happen like, if so there is a way like you can involve this top down feedback with perfect inverses, no problem, but the brain does not do it. So there is like another way of looking at this argument, and that is something which is known as random feedback weights. And what it means is that basically, let's get around the assumption that you need to calculate the weights at all. You don't need to calculate backward weights as perfect inverses. So let's say like you have weights which are like during forward pass you have like these forward set of weights, and during backward pass, let's say you don't have perfect inverses but you have some random weight wb dash. So you have like some random weights, and then you still like enforce this sort of constraint. Like when you pipe in your input activity x, you get h1, h2, h3, and then you get y. You get this back, and then you reconstruct like h3, h2, and h1. So let me call this h3 dash, h2 dash, h1 dash. And now if like during the learning process you are actually enforcing h1 and h1 dash to be close to each other, and similarly h2 and h2 dash close to each other, and h3 and h3 dash to be close to each other, you can easily do that. But the key point is like in this case, if you do this sort of like target approximation, and you learn the weights of your backward net wb in such a way that the above condition holds true, then it is possible to show like the essential weights which your network learns are actually the inverse of the forward network. So like you don't need to perform an explicit inverse operation to initialize this backward weight matrix, but then you can just learn it via gradient descent. And it turns out like what you learn mostly is like an approximation of the inverse operation. So that's so it has been found like this is really true in practice. So during training this kind of network, you can just initialize the top down network by some random weights, and then the bottom up also with some random weights. But then overall like the network will learn such kind of representations in which like the random weights essentially become equal to like the inverses of the forward weights. and even if they are not, but still like the network manages to converge and reaches a real good performance, and that gets around the problem that in the brain, like obviously the brain does not compute this sort of inverses, perfect inverses, but then there it computes something. It can compute like some sort of thing which is close to the inverses, which is essentially getting the job done. And the whole idea for bringing like this top down and bottom up feedback along the way is because now you can get rid of the problem of storing like the intermediate activities while you are updating your neural network. So essentially, let's have a look again at the kind of problems of backpropagation which I was talking about. Okay, so if you look at this slide, what this essentially means is that by bringing in some sort of like bottom up network, top down feedback network, you can essentially if you have like final activity yi, you can reconstruct xi on the fly, and then you don't need to do like this kind of, you don't need to store like xi or yi anymore. And the problem just comes down, so you can get rid of these two assumptions also, which are the limitations of like backpropagation, that you don't need to store these xi anymore, assuming you can learn this top-down neural network in a very good way. So let's assume that you can learn this top-down neural network in this way. So then the key problem is that what does like the entire algorithm start looking like, and that is what like I want to talk about next. Okay,